We shall now present advertisement problems in social networks, and we shall begin with a semi-dynamic one. By that I mean that we are concerned with decisions that will influence the whole dynamics, but will be taken once and for all in the beginning of the advertisement. We consider a finite target population M. We already saw before that finite population models, which are unviral, produce indeed exponential concave increase in the number of views. So we assume that there are competing sources of information. We assume that a potential destination is only interested in the first content it receives. For example, if it is interested in a hotel list, if it gets it from one source, it will not be interested anymore in getting it from another one. Or if it looks for a flight ticket and reservation, then it will not need to re-reserve it elsewhere. Let X of int be the number of copies of the content at the destinations from source I at time t. And let xt be their sum over the different players I. We denote by lambda I the popularity of content from source I. What is the popularity here? It is the rate at which destination nodes receive content from source I in the absence of advertisements. We define lambda to be their sum over all the i's. Next, we describe the dynamics of the system. The rate at which the number of copies of the content from source I increases is proportional to the number of destinations that don't yet have the content altogether. So it's m minus x of t, multiplied by the popularity scale. So by the lambda I, which is the popularity of source I. If we take the summation over all i's, we get the following differential equation. The rate at which the total number of copies increase in the system is proportional to m minus xt, to the number of destinations that don't yet have a copy of the source. The scale factor is lambda, which is the sum of the popularities from all sources. The solution of this differential equation is exponential, as we already saw. Now, if we substitute it back into the first equation, then we get the following. So the solution is given by the formula that you see there. At time 0, it is just xi0, whereas as t goes to infinity, it converges to m times the ratio between lambda I and the sum of all lambdas. Here is an example of a curve obtained when using this exponential model. It is obtained for a total population size of 400,000 and for a zero initial state. The mathematical model that we developed with the concave increasing exponential curve, along with the numbers that we took here, turned out to be a good fit to the example that we already saw before of President Obama singing Sweet Home Chicago, which you see here. We now present a game formulation of the problem. Our starting point is the formula for the time evolution of the number of contaminated nodes or nodes that have copies from the content of source I. This is what precisely node I wishes to maximize at some very large time. So let us look at t goes to infinity. Then the number of copies originating from source I that arrive to the destinations is given by the ratio between the popularity of content from I divided by the sum of popularities of all contents, time m, which is the number of destinations. Now consider advertisement decisions. By advertising, a player can accelerate the rate of dissemination by a constant factor. In other words, it multiplies the popularity lambda I by the chosen variable AI. AI cannot be smaller than 1. Because if we have no acceleration, then it is simply 1. This acceleration is obtained at some cost. We assume here a linear cost, which is given by a constant g times AI minus 1. Again, the minus 1 is there because we don't want to have to pay anything if we don't accelerate, if we don't advertise. Now the utility for player I is simply the difference between the dissemination payoff x of I at time infinity and the advertisement cost. Now instead of writing g times AI minus 1, we don't write the minus 1 since that part does not depend on the action A. So it is a fixed cost that does not depend on the decision. The equilibrium that we get here is the same if we write or we don't write this minus 1. The game now consists of a choice which is done initially at time 0 of the multiplicative factor AI by which we accelerate the popularity of each one of the players I. This static choice induces a dynamics of X. This is why we call it semi-dynamic. It's the combination of dynamics that we get from a fixed choice in the beginning. We now write small u of I as the product of AI and lambda I. So small u of I is the popularity of players I content after it advertised them, after it multiplied lambda by a multiplicative factor AI. We denote by u the sum of post-popularities, of the sum of these u's. So the utility for player I can now be written as some constant Ri times the ratio between ui and u minus ui, where this constant is simply m times the initial popularity before multiplying by AI divided by g. Now we already saw such games in this tutorial. It was the generalized Kelly problem simply. So we can view ui as a bid which we pay for, and our utility is proportional to the share that we get. We can now apply all the machinery that we had there, and in particular, it turns out that there exists here a unique equilibrium in pure policies, so we don't need to randomize here, that we can compute this equilibrium by solving an equivalent global optimization problem, since this game tends to have a potential, and any best response sequence converges to the unique equilibrium here. We now have a look at the properties of the equilibrium. The equilibrium value of the policy of player I, the choice of popularity, are obtained by maximizing the utility of player I. Now, assume that this maximum is an interior point. Then it is obtained by differentiating with respect to ui and substituting 0. And this is precisely what we do here. We then see that the product of Ri and u minus ui do not depend on I, are the same for all I. It directly follows that ui is increasing in Ri in order for this product to be a constant in I. Of course, the equilibrium can also be on the boundary, and in that case it's the action A, their initial acceleration is just 1, so that ui equals to lambda I. So except for the boundary, everywhere else it's ui is in fact strictly increasing in Ri at equilibrium. And this means that we accelerate more if for those contents that are more popular, because Ri is proportional to lambda I. It is also increasing in M, proportional to M, which means that there is more incentive to advertise if the potential interested population is larger.